Okay, so today's recitation is going to cover all of homework 10 because it's going to actually be due on Thursday. It's going to be due right before your second exam. So yeah, we'll be able to finish all of this, and we'll probably finish early. So yeah, what we are covering today is about the topic of L'Hopital's rule. So I'll say some words on what that is. So L'Hopital's rule has to deal with if you have a particular limit that looks like this particular format. So you have a fraction, so you can just take the numerator to be a function, the denominator to be a function. And the key thing is that if this is of the form 0 over 0 or infinity over infinity, if when you actually just naively plug in and try to calculate the limit, you have either of these two indeterminate forms, then L'Hopital's rule says that this limit is equal to the limit if you were to take the derivatives of the numerator function and denominator function. So you end up constructing a completely new limit. And it's saying that this original limit is equal to this new limit. And yeah, this process can only be applied in the circumstance that you have one of these two indeterminate forms. If you have something else, then most likely, like, you should be using something apart from L'Hopital's. Usually, like in that case, usually L'Hopital's would actually give you the wrong answer. So you have to be sure that you actually have one of these two types. So I'm just thinking like, oh, what if the whole thing is infinity, or the whole thing actually is some constant? Like it could be 0 over like a constant, which would then be equal to 0. In such circumstances, you should know that the whole limit is equal to 0. Okay. Another thing I want to say is about the whole list of all the indeterminate forms. So there's, I think, a list of 7 of them. So to start with, there's the 0 over 0 and infinity over infinity. Then there's 0 times infinity. And the idea is that you can get from 0 times infinity to either of these two by just reciprocating one of the two products. So if you reciprocate the 0, then 1 over 0 is kind of an infinity, so you would get infinity over infinity. If you were to reciprocate the infinity, well, 1 over 0, or 1 over infinity, is kind of like a 0, and so you would end up with 0 over 0. So going from this product to one of these two is just by reciprocation. And then there's 3 different ones that you can get to. So let me see if I can do this. I think it's 0 times 0, infinity times 1, or no, maybe infinity times 0. Yeah, and I think 1 times infinity. So yeah, I'm pretty sure that's right. So the way that you go from any of these 3 to 0 times infinity is you take the logarithm function. Okay, so that's just going to pull the exponent down. You take the log of the base, and it will convert into 0 times infinity. And that's how you kind of remember those 3. If you have an exponential kind of thing where when you take a log, you end up with 0 times infinity, then the thing that you started with was an indeterminate form. There are things that kind of look like these 3 that actually do have well-defined values. Right. Remember that an indeterminate form is a special quantity that you can't really assign it a single value because it depends on context what the value that you would assign, what that value should be. That context is like what the actual functions are. Like, how are you approaching 0? How quickly are you approaching 0? How quickly are you approaching infinity? And 1 in this case. Okay, so those are 6 of them, and then the very last one is kind of a bit of an outsider. So it's infinity minus infinity is the very last guy. And usually the infinity minus infinity shows up as being like a fraction minus a fraction. So what you would normally do is you end up just subtracting the two guys, and then I guess that in a way like it directly goes to this, but it's a bit it feels a bit different. So I don't really want to directly connect them. But so these are all of the indeterminate forms, and we'll encounter, I think, all of these kinds in the problem set. Okay, any questions so far? No? Okay, right. So yeah, well, part A, I guess. We could just do this with algebra, but since we're doing L'Hopital's, we should probably try to use L'Hopital's. So if you were to naively plug this in, you'd get 9 minus 9. You'd get 0 on top, and you'd get 0 on the bottom. I should mention, like, you should always check whether or not you can use L'Hopital's before you actually use L'Hopital's. And when we grade, we will be looking for that check, that confirmation that you actually can use L'Hopital. So make sure that you write it somewhere. Usually you should write it like somewhere close by. Don't just like write it in the corner somewhere. Okay, so yes, we plugged in, we get 0 over 0. That means we can use L'Hopital's. And so I'm just going to now create a new limit from where I take the derivative of the top and the bottom. So derivative of the top is going to give me 2 times 3 plus h. That's going to be it. And the denominator is going to be 1. Okay. Now I can plug this in, and I'm going to get 6 is my answer. And so 6 is my answer for the question. Then it says something about it matching. So this is kind of just saying that this limit is actually coming about from a limit definition of derivative. You can kind of check that this like satisfies the limit definition of this derivative. And you can verify that this is like the answer you'd expect by just taking this derivative and plugging in. That verification is up to you. I don't think that it really adds very much, so I'm gonna skip over that. For part B, well, if we directly plug in, notice that we're gonna have cosine pi over 2 minus cosine pi over 2. So we're just gonna get 0 over 0. So again, we can just use L'Hopital's, and this time it's theta goes to pi over 2. And we take the derivative on top. That's going to be minus sine of theta, and then denominator is going to be 1. Okay, so now we can just try to plug in. Well, what is minus sine of pi over 2? Well, pi over 2 is 90 degrees is going to be 1, so negative is going to be negative 1. And so we get negative 1 for part B. Okay. For C, well, when we plug in, we get 0 over 0. So we can use L'Hopital's. So go ahead and do that. And here we have a chain rule. So cosine of theta, oops, make that a bit larger, times 2 theta divided by 2 theta. Notice that now the 2 theta will cancel. And then the resulting thing I can just plug into. So I'm going to get cosine of 0, which is 1. So I can just box that. Okay. And then for D, in this case, you can kind of guess that you're going to need more than one application of L'Hopital's. So if we were to plug in at this juncture, we would have infinity over infinity. So we just go ahead and apply L'Hopital's once. So the derivative of the numerator is going to be 6x plus 8 over e to the x. But then if you try plugging in here, you're going to get infinity over infinity still, which means you can apply L'Hopital's another time. And this is going to give me 6 over e to the x. And then here, when we plug in, we're going to get 6 over infinity. But 6 is a constant, and infinity is really large, so the whole thing is going to approach 0 when we actually do this evaluation. All right. So yeah, it's important to note, like, yeah, if you can apply L'Hopital's more than once, you probably should. I know some people will make the mistake of stopping at this point and saying like some nonsense like infinity over infinity equals 1 or something. That's very much not correct. You have to continue going until you get to something that isn't an indeterminate form that you can actually conclude something about, which in this case is here. So yeah. All right. Any questions on this page? No? Okay. All right. Then we have 4 more problems, 1 more page. For E, notice that this is of type 0 times minus infinity, but whether or not the infinity is plus or minus doesn't really matter here. So it's of the type 0 times infinity, and what we need to do then is we need to reciprocate one of these 2 things so that we get something we can apply L'Hopital's to. And there's only one choice of what we want to reciprocate here. The only thing that we could possibly want to reciprocate is the x squared. Because if you try to reciprocate ln of x, you're just going to get something really messy. It's much easier to just reciprocate the other thing. All right, where's my cursor? Okay, so first we start with just an algebraic step. We rewrite the x squared on top into a negative x to the negative second on the bottom. And in this case now, we have infinity over infinity. You can check, which means we can use L'Hopital's at this point. And so then we take the derivative, and derivative of ln of x is 1 over x. Derivative of the negative second power is going to be negative 2x to the negative third. And we can just rewrite this algebraically. So just imagine that you multiply maybe top and bottom by x cubed, and you see that you're going to get a negative 1 over 2 and then x squared. Right? So that's just a bit of algebra. And we can lastly just plug in. So we end up with 0. Okay. Now f is where things start to change a little bit. Well, f and g are slightly different. So when you have one of these limits where the indeterminate form is like an exponential type of thing, there's a different process to do this. Firstly, let's just check what this type is. So it would be 1 to the infinity. And you can think through in your head that if you take the logarithm of this, you're going to have infinity times log of 1. Well, log of 1 is just 0, so you would get infinity times 0. So this isn't an indeterminate form. What you need to do is the primary way that we teach you how to do this is to set the limit equal to some value L that you don't know about yet. And then you take the logarithm of both sides. That way, what you end up calculating ends up being ln of L. And then you later on recover the value for L by just exponentiating both sides back. So we go ahead and we take the logarithm. And when we take the logarithm, the exponent is going to drop down. That's the whole point. So we end up with this as our new limit. And if you were to plug into this limit, you'd see you get infinity times 0. Well, that tells us that we need to reciprocate one of the things, and the only thing that would make sense to reciprocate is the x. So we're just going to do that. So I have not done L'Hopital's yet. I'm about to do it now. So just as a final check, we see that if we plug infinity in, we're going to get 0 on top and 0 on the bottom. And this is completely fine for us to use L'Hopital's. So we go ahead and use it. Okay, so now we get derivative. And this is a little bit messy. The derivative of the inner function is going to be 2 over x squared. And then the denominator is going to be, well, don't really need to say -1. It's just negative x to negative second. Okay, now we have to simplify this a little bit. The easier way for me to explain this is just imagine multiplying top and bottom by x squared. That's going to cancel this part with this part. And so then we end up with an expression limit of -2 over 1 minus 2 over x. And then you can actually evaluate this. So plugging directly in, you get -2. Okay. And I can make that a little bit larger. But notice now, what did we actually solve? We found ln of L is equal to -2. So what we found is ln of L is equal to -2. Therefore, the original L that we're looking for is the exponentiate both sides, so e to the -2. And so this is the answer to the problem that we were originally asked. So you can solve these types of problems in this way. And I think this is the way that Spencer explains it as well. So there's a slightly different technique where what you do is you use the property that e to the ln of x. Like there's a particularly sort of strange looking approach where what you do is you use this identity to rewrite things. It sort of is a more, I guess, it's a way of like avoiding creating the variable L, but it forces you to introduce an exponential and a logarithm at the same time. Whereas here what we do is we just declare that we're going to take a logarithm and then exponentiate later. Like this is just trying to collapse these two things. I don't know, you may come across solutions that write things in this way. So I'm just trying to mention that. Anyway, for G, we can use the same approach. So we set the whole problem equal to L, and we take logarithm of both sides. Which will give us this. And then if you plug in, maybe we should have plugged in the beginning. So plugging in the beginning, we see 0 to the 0. If you take log of that, you're going to get 0 times infinity. So this is an indeterminate form. And this is 0 times infinity. What we need to do is reciprocate something, and there's only one clear option. And so when we reciprocate, we're going to do it like so. And now when we plug in, we're going to get infinity over infinity, which is great because that is an indeterminate form for which we can use L'Hopital's. So we can go ahead and use L'Hopital's. Okay, then this is going to give me 1 over x here, negative x, negative second there. And then if you just imagine multiplying top and bottom by x squared, you're going to get x on top and then, well, negative on the bottom. So there you go. And so the whole thing we got is ln of L is equal to 0. And so L is equal to e to the 0, which is 1. So I want you to know that e to the 0 is 1. I see a lot of people in past recitations, I've seen people write e to the 0 and not know that that's equal to 1. I think it's very important that you know something as simple as that. Okay, so I should be able to evaluate something like that. Okay. Any questions on this process? Because the last problem, H, is slightly different. Yeah, okay. All right. Yeah, so h. So if you plug into h, what you would get is you see a 1 over 0, which is infinity, minus 1 over 0, which is infinity. So you end up with infinity minus infinity for this. And this is, it's always rare to find these infinity minus infinity things. And this one is kind of more complicated than normal. So it's like nice in that regard. Okay. So, well, the only thing you can do for this is you can try to combine the two fractions. And so we go ahead and try that out. Just put everything over the common denominator, just subtracting fractions. And when you see this and you try plugging in, you're gonna get 0 minus 0 over 0 times 0. Well, 0 times 0 is 0. It's one of the facts that we actually are certain about. So this is actually 0 over 0, which means we can use L'Hopital's. Okay. Well, the derivative may not look quite so nice because the denominator does require the usage of product rule, but we can still go ahead and do that. So we get ln of x plus x minus 1 over x. Okay, right. Now if we try to plug into this, we're going to get 1 minus 1 over 0 plus 0. So we get 0 over 0. So we can use L'Hopital's one more time. Okay. Well, taking the derivative of this negative 1 over x is going to be positive 1 over x squared. Ln is going to be 1 over x. And then to deal with this, the easiest thing to do is actually to rewrite this. So that x minus 1 over x, I would just split the denominator over both things in the numerator. And so then I can just take the derivative of that very easily. So then get 1 over x squared. And at this stage, I can plug in just fine. So I'm going to end up with a 1 over 2. And lastly, we just look back and we notice we were solving for the original problem, not ln of L. So we can go ahead and box this guy. Okay. So that's the whole problem set. Are there any questions on anything?
Can you go back to C? I just want to look at that one real quick.
C, okay, yeah. Yeah.
Okay, I see what I did. Thank you.
Okay, sure. Yeah. All right. So yeah, exam is on Thursday. If you wanted to ask me anything, I guess actually wait, we have recitation done, don't we? Okay, yeah. So I guess you can ask me questions then. Otherwise that's it for today.
Actually, I have one more question. I sent you an email.
Oh,
I don't know if you saw.
uh,
Okay.
I can check.
Okay. Yeah.
Can you ask me now? Yeah.
Yeah. Okay. So last week you went over 9, and you got x equals 4